Hello, everyone. Thank you for joining me. My name is Kiril Solovey, and I'm from Stanford University. Today, I'm going to present our work on revisiting the asymptotic optimality of RRT star. This is joint work with Lucas Janson, Edward Schmerling, Emilio Frazzoli, and Marco Pavone. Our work focuses on the highly popular algorithm for sample-based motion planning termed RRT star. RRT star constructs a tree embedded in the configuration space of the robot in order to uncover a collision-free path taking the robot from its origin to its destination. An important property of the RRT star algorithm is that it constantly strives to optimize the quality of the solution returned by rewiring the tree around random samples that it introduces. The importance of RRT star lies not only in the fact that it runs remarkably well in practice, but also due to the fact that it comes with strong theoretical guarantees. In particular, Karaman and Frazzoli showed in their influential work that RRT star is asymptotically optimal. That is, it is guaranteed to return a solution that tends to the optimal solution as the number of samples tends to infinity. However, in our work, we call this theoretical result into question. In particular, we identify a logical flaw in the original optimality proof, which deems it to be incorrect. In our paper, we demonstrate that the conditions for optimality which were used in the previous work are in fact insufficient, and we construct a counter-example showing that even when those conditions are satisfied, RRT star may return a solution of suboptimal cost. Before we get more into the details of what went wrong in the previous proof, let me briefly go over the details of the RRT star algorithm. So the algorithm constructs a random tree that is embedded in the configuration space of the robot. In every iteration of the algorithm, it generates a random sample and attempts to connect this random sample to the tree in the following manner. It considers a radius R ball around the sample, where R is the tuning parameter of the algorithm, and it will connect one of the existing vertices of the tree that fall within this radius R ball to the new sample in order to minimize the cost of reaching the red sample. In this case, RRT star will add the blue edge. Next, RRT star within the same ball will attempt to rewire existing connections in order to improve the cost of reaching existing vertices in the tree. Particularly in this specific example, it will add the connection between the red sample and the blue sample with the green edge, which will improve the cost of reaching the blue vertex. Additionally, it will remove the redundant edge that was previously reaching the rewired vertex. Now we are in the position to describe what went wrong in the original optimality proof. The previous proof utilizes a ball covering argument that goes as follows. The proof tiles the optimal solution to the problem using partially overlapping balls, where the size of those balls is slightly smaller than the connection radius that I just mentioned of RRT star. It then shows that it suffices to reason about the locations of the random samples with respect to those balls in order to prove or disprove optimality. In particular, the authors derive the following conditions for optimality of RRT star. And they show that if every ball contains a random sample and there is a pairwise ordering between those samples, then RRT is guaranteed to return an optimal solution. So what do I mean by a pairwise ordering? This pairwise ordering is concerned with every pair of consequent balls within this construction. So let's just consider the fourth ball and the fifth ball, and a pairwise ordering holds if the sample that lands in the fourth ball came before the sample that lands in the fifth ball, namely that the indices of those samples are in increasing order. That is, I came before J. The motivation behind those constraints is that RRT star will be able to gradually reach from one ball to the next until it eventually will reach the final ball and will be able to connect to the target configuration. And due to the construction of those balls and their size, the quality of this solution will be very close to the quality of the optimal solution. However, this proof overlooks the fact that pairwise ordering does not necessarily imply full ordering. So what do I mean by that? The fact that I comes before J and K comes before L doesn't necessarily mean that also L came before I. So this is the main issue with the proof. Our main contribution in the paper is that we were able to develop a new proof for optimality, which is able to overcome all the limitations of the previous result. The way that we do that is by replacing the pairwise ordering constraint with a full ordering constraint and deriving the conditions for which such a full ordering constraint would hold. To accommodate this stronger condition of full ordering, we require a slight adjustment to the connection radius that is used by RRT star. In particular, the previous proof derived the following connection radius that is used for the rewiring. It is sine constant times log n divided by n to the power of 1 divided by d, where n is the number of samples and d is the dimension. Our proof suggests that this connection radius should be actually a little bit larger, where the exponent in our case is 1 divided by d plus 1. So the exponent is a little bit smaller, but overall the connection radius is slightly larger. In the future, we're planning to explore whether this connection radius can be reduced in order to improve the construction time of the RRT star tree. So to summarize, in our work, we highlight a logical gap in the original optimality proof for RRT star, but we're also able to present a new and revised proof that overcomes this logical gap. If you have any questions or remarks, don't hesitate to contact me or the other co-authors. Thank you for your attention, and bye-bye.